Cool. Okay, so again, welcome everyone to Paper Club organized by nPlan. Today we're going to be talking about a topic that we don't discuss much in Paper Club, which is reinforcement learning. So there are a few, I would like to start with a few refreshers on the parameters in reinforcement learning and what is involved in reinforcement learning, just so that we're all in the same page. And then we can dive into the paper, which I found really interesting because they solve a long-standing problem in reinforcement learning, which is how to efficiently solve imperfect information games. So on that note, the first point of the refresher is that there is some game theory involved here about what is a perfect information and an imperfect information game. So the main point here is that in a perfect information game, all the knowledge about the game and the possible outcomes is known to all the players of the game. So if you think about a game like chess, at any given point in the game, both players know what is the position of the board, and both players know what are the probabilities of outcome for all the future possible moves. Of course, this is in the ideal case, but we must only know that both players have access to all the information. An imperfect information game is when some information is known only to some players. And one of the most popular examples is poker. So there is some public information, like the cards that are on the table, and there is some information which is only known to some players, which is the cards that that each player sees. So the private cards of each player. And one of the interesting bits about the paper, and we'll go into detail in a moment, is that they convert an imperfect information game into a perfect information game. And what they claim is that if you can make this this trick, you can apply this rebel network to solve almost any imperfect information game with some dimensionality restrictions. Okay, so the other bit that I wanted to do a quick refresher on was on reinforcement learning. So what's the problem setup and what are the what's the common terminology used in reinforcement learning? Let me just share my screen. Okay. Okay. So you should all be seeing my screen now. Let me just open the chat. Where's the chat? Okay, cool. Just to keep an eye on the chat in the beginning. Okay, so on the broad sense of the problem, the task that we want to solve in reinforcement learning is that we have an agent, and an agent is going to be our machine learning model, which we wanted to do something, but this something is going to affect an environment, and the environment is something that we have very little control of, but it has a specific behavior. So if you think about chess, for example, the agent would be a player in chess, and the environment would be the chessboard and the rules of chess. So the idea in reinforcement learning is that the agent will perform an action, and that action is going to change the environment. So it will take the environment to a new state. So an action for one player in chess can be move a piece to another position. And there are a number of legal actions in chess, and those actions affect the environment.
Can I ask, sorry,
yeah.
In chess, is the other player already part of the environment in this one?
Well, that depends on how you define it. So we'll get into it in a moment, but chess can be defined as a one-player game. So your agent is the only player in the game, and it is just reacting to changes in the environment. In that sense, the other player would be the new state. So you make an action, and then the other player gives that action changes the environment, and the environment responds with a change, another change in the environment.
Thank you.
No worries. You can also frame, which is one of the big issues here with this paradigm in reinforcement learning, is that you can also frame reinforcement learning as a multi-agent problem, but we'll get there. So very quickly, the environment is defined by a state. And that state can be, if we continue with the chess analogy, the state can be where are all the pieces in the board. The action will depend on the state of the environment. So the action that the agent will take will depend on the state of the environment. And what is one of the key parts of reinforcement learning is that there is a reward. And what that means is simply that there is going to be some numerical value that the environment will provide based on what was the state that the environment was in, the action that the agent took, and the new state of the environment. You can actually extend this reward to include the future action of the agent, but let's just keep it simple for the moment. And the agent is going to use this as a means to assess whether it is taking good actions or bad actions. And we get to the policy, and the policy is what you would actually call the agent. So the policy maps a state into an action, into a space of valid actions, and the policy can be deterministic or it can be stochastic. Of course, in all modern reinforcement learning, the policy is some probability distribution over legal actions, and this policy is what will define what this action is going to be. And well, based on these things, we can define the return. The return is the long-term reward. So if you think about knowing the whole game, you can map out all the following actions that you would take, and you can calculate a return function. And this is going to tell the agent in a supervised environment, of course, not at test time. It's going to tell the agent, well, the policy that you're doing is good now, but maybe it's going to be really bad in 5 moves from now, or it's going to be really good in 2 moves, but then it's going to be really bad. So this is how the agent knows if the policy is a good next best action or if it's a good global policy, so a good policy in general. And what we are most interested in for most reinforcement learning applications is what you call the value function, which is the expected value of that return. So it's the expected return given the current state of the world and a policy. What is the expected return of your policy? And you can also define it as action value, which is called Q, which depends on both the state and the action that you will take. You calculate the future expected return. And so what is very interesting in, well, before we get there, probably the biggest assumption in reinforcement learning is that it only applies to when you can frame it as a Markov decision process. And that just means that the next state, so the state at t+1 depends only on the current state and the actions that you take at that state. So you can define it like this as a chain of events. And this assumption is what enables most of the reinforcement learning algorithms. And one final note on reinforcement learning is that these value functions, you can of course, the value function or the Q function, you can of course define them by a mathematical formula. So you can explicitly write what is the expectation of the return and write a function for the return. But in reality, this is not done anymore. Modern reinforcement learning techniques use a neural network to calculate this value. And this is where it gets a bit confusing, because there are a bunch of places where you will see, okay, the value is the expectation and so on, and you will see a whole mathematical formulation around it. But in the end, it's a neural network, and at each iteration of the reinforcement learning algorithm, so every time the agent produces an action, you do some gradient descent or gradient ascent algorithm to verify that your value function is being calculated properly, and the network gets better at calculating the value of your actions. Cool. So that brings us to this paper, which is trying to solve a long-standing problem in reinforcement learning, which is that what happens when, well, first you don't have a single agent working in the environment, but you have multiple agents. And what happens when the process is not perfect information? And the big issue with an imperfect information game is that if you want to calculate all the future states or all the future possible states of the world, eventually you need to have all the information about the environment and about all the policies. So this is what this paper is about. It's okay. How do we solve the imperfect information game problem? Okay, cool. So let's go a bit into the setup. So we do need to make some adjustments to our definitions so that they fit this new setting. But in reality, the concepts are the same. So we will now have 2 agents instead of, well, the whole paper is solved for 2 agents. So they say that you could eventually generalize for more agents, but all the proofs only hold for 2 agents acting in an environment. So if you think that you have 2 agents, your actions are no longer going to be a single set of actions, but they're going to be the joint actions of both agents. So the actions are going to be a tuple of actions taken by the agent. The worlds, so the state, the environment is still represented by a state, but now this is called the world state. And something that we need to define in imperfect information games is that the world is going to produce rewards for each agent, but it is also going to produce a set of observations. Some informations are going to be public and some information are going to be private to each player. Now, because this paper converts from the imperfect into the perfect information game, and we'll see how they do that in a moment, let's just assume that all the observations are going to be public, and that's just going to make things from now on a bit easier. A public observation is defined by the state that the world was in, the set of actions that the players take, and the new world state. And there's a transition function between this world state to this world state via some actions. Okay. Then, of course, we can define everything in these terms. So there is a history which is actually important. And again, we can think of the history in very general terms where there are public and private observations. But for a moment, let's just assume that a history is going to be given by the world state and the actions. And then you have your info state, which is also going to be defined as part. So a given history is going to have an info state, and that info state are observations and actions at every stage. And again, just for simplicity, let's assume that we'll only be keeping the public observations. So we will concentrate on the public state of the world. Okay, is it clear that the public state of the world is composed of the state of the world and the actions taken at every point? Yeah. Okay.
The actions are themselves part of the state, or are the actions part of the transition from one world state to the next world state?
The actions are part of the info state. So yes, they are part of the, well, in this case, what they call the info state. So
and the agents choose at the same time, right? So it's
yeah. Cool. And the other generalization. So all this part, so this whole paragraph here, it's fairly convoluted. If you want to understand it, I invite you to read it. It's actually very interesting on how you define the whole info state and so on for imperfect information games, but it's actually not relevant for what they do later. So let's just skip it for the moment. And the other thing that we need to know is that each agent is going to be updating its own policy. So we actually have 2 agents, and that means that we have 2 policies. But in order to make things provable in general, we define a policy profile, which is just the combination of all the players' policies. Now, they also make a further assumption that this only applies to 2-player zero-sum games, and the mathematical definition is that if in 2-player zero-sum, if one player, where is it? Well, anyway, if one player receives a reward, automatically the reward for the other player is minus the reward for the first player. And the last concept in this paper is that of Nash equilibrium. So in perfect information games under 2-player zero-sum, Nash equilibrium is the best possible policy for every player, and it just means that, well, that is the definition. It means that no player can change their policy to get better return or to get better value. So that is what it says here.
Sorry, that is actually quite interesting one, right? Because it's not necessarily the globally best state. It just means that if both players adhere to that point, no one can move. But it doesn't, I think, necessarily mean that if they wouldn't agree, they could get both better in general information games. So it's a local property, right? It says something about not the whole game necessarily as a whole, but just about the local state of the game.
Yeah, it means that each player won't change their strategy. So each player is playing their strategy, and that's the best strategy they can play given the other players. There might be a better global option, but players can get locked into into a Nash equilibrium because it's balanced and it's stable, but it's not the best situation they could be in.
Yeah. So yeah, that's very good, and we'll see later why we want Nash equilibrium. But in a nutshell, because the agent is going to be deployed in the real world, the best possible policy for the agent is to assume that the contestant is also playing their best possible policy, and that in turn gives, because in real life it's actually very infrequent that people play with their best possible policy. The agent is always going to be playing a better game than the contestant.
Nice.
Yeah. Which is this is actually quite. I read a couple of papers, and so they always assume that that you're trying to reach Nash equilibrium, which is interesting. Okay, and well, the last bit is that, well, if you think about the game of chess, or specifically the game of chess, if you want to simulate the whole game, you have way too many options. So what you usually do in reinforcement learning is you define a sub-game, which means that assume that you start at some point in the history, play that game instead of having to play it from scratch every time, and that speeds up the learning process. And not only does it speed it up, but it actually makes it tractable. Otherwise, you can't optimize the model. And also, a depth-limited sub-game is a further assumption. Again, if we think of chess, at every possible move, there are hundreds of next possible moves. In a depth-limited sub-game, you just say, okay, as an agent, you're just going to compute the value 2 steps ahead, or 3 steps ahead, or 50 steps ahead. And you're going to try to compute the value at that point. So don't get to the end of the game. The optimal solution for any reinforcement learning algorithm is to use the full game, because you are computing the true value of the action, but in reality, this is intractable. Okay, and now comes, after all these definitions, if there are doubts about these definitions, it's good that we resolve them now. Otherwise, it's going to be, because everything follows very quickly from now on. Okay, cool. So the question is, how do you go from a Okay, so the question is, how do you go from an imperfect information game to a perfect information game? And this is where it gets really interesting, because so in the normal game of poker, each player receives a card and the other player cannot see this card. So that's what makes it an imperfect information game. And based on the card that they see, or the couple of cards that they see, they have one of three actions that they can produce. So in this setting, we cannot solve poker, or it is not tractable to solve poker. But then they say, okay, let's think of a different game. So think of a game where neither player can see their cards. All they can do is make public what they would do if they had a card. And there is a referee who is the only one who is allowed to see the cards. Now, what each player does is they make their policy public. So they say, okay, if I had an ace, I will play with this probability check, with this probability fold, with this probability raise. If I had a 2, this would be the probability over my actions. And if I had a 3, this would be the probability. Same thing for player 2. They make their policy public. And this policy can be different from this policy. The referee then is in charge of taking the actions, of actually taking the actions based on, okay, the player says, the referee sees the card. Neither player sees their card. Only the referee sees the cards. This player says, the referee says, okay, you got this ace, you're going to take this action. Player 2, you got this card, you're going to take this action. But still the players don't see the cards. And the only thing that the players can see are the public information. So the cards that are public, not the cards that are lent to themselves. And they can compute the probability that they have a given card. So everything that we saw up until now from reinforcement learning environment, it was all very much deterministic. Now everything becomes stochastic. So instead of having a world state, you have a probability of world states. And that is what they called the public belief state. So if you think about a state of the world under some public information, or under some public info state, well, now your public belief state, which is what we're actually going to use to optimize this agent, is going to be the probability of being in a state given the public information. So for the specific case of poker, the public belief state says what is the probability that player 1 has this card, this card, this card. So it's going to be 52 probabilities for player 1. And the same for player 2. What is the probability that player 2 has all of those cards? So now you have a sampling space of where you might be in the state of the world. Now, the claim that they make in the paper, which if you reason about it enough, is that these two games actually have the same optimal strategy, which is interesting because it means that if you want to play poker properly, you should not see your cards. You should just be working with the probability that you have a card and then take an action based on that. So that's the state of the world now. Is that clear? Cool. Okay. So from this, actually, all the mathematical definitions follow fairly quickly. There is one caveat in that you can actually calculate the total value for any given public belief state. You can calculate the entire value, but in practice, so you can calculate the entire value of a policy, so the expected return of a policy. In practice, this is not possible because if you think about so you have 52 probabilities, and then for each card you have 3 probabilities of actions. In reality, in the actual implementation, your actions are much more continuous than that because you can raise in different ways and so on. So this is actually intractable. What they do is that they calculate the value for each info state, or for a sample of the info states. So what they prove in the appendices is that optimizing this. well, I just erased some stuff. Okay, is that optimizing this actually approximates Nash equilibrium, even if you're not directly optimizing this. So that is the setup of the problem, and of course the big question and the big answer from this paper is, well, okay, if you're going to just work on, if you're just going to estimate the value on some info states of the entire world, of the entire set of possible info states, how do you choose them? We'll see in the results that choosing them at random is actually not a good idea. Because the agent doesn't learn anything useful. But instead, what they do is they restrict the game and compute value in only sub games of the state. So imagine you have a public belief state. So you have all these possibilities, which say, okay, what is the probability that player 1 has this card, the probability that player 2 has this card based on the public information, and so on and so on and so on. Take a sample from one of those from that public belief state. So get one of the possible info states and play that game. And you play a depth limited game. So you play that game, calculate the value of the leaf nodes, and update your policy based on this game. For the next iteration, you're going to choose one of the leaf nodes and repeat the process. So now assume that you're in this info state. What is the next optimal policy? And you update the policy in this way. Now, remember that the value of these leaves is actually computed by a neural network, which means that once you compute all these values, because you know the rewards, so you know how to compute the values how to compute the actual value of a given policy, you can put all of these, so all of the values that you saw here and the respective info state, you can put them in your training set and use that training set with the set of values to train your value network. So in reality, you have an optimization around another optimization problem, right? So you're assuming an info state, finding out the value of these things, using that info state and these values to calculate the loss over on the value network. You do some gradient descent to optimize your value network. Then you go to the next node, assume the game again, compute all the possible outcomes of the game, and update your value network again.
So that does only work because poker is a relatively quick game where you know in 1 or 2 steps already whether you have made or lost money. I could imagine if these steps would go much deeper, say 100 steps deep, because a game of poker would have 1,000 cards and you have to open up 100. That would still be, because at some point you have to have the information pushed into the system of whether you actually won at some point, right?
Yeah, and actually, in fact, what I just mentioned is not possible in poker either. There are, because you have probabilities over probabilities over probabilities, and you never know which cards you have. Finding all the leaf nodes is actually intractable. So you need to. So that is where the search part comes in. So it's reinforcement learning plus search, and the search part is how do you optimally choose these leaf nodes, or which info state or which actions to take that will take you to info states of the game that will have useful information for you to update your values. And they use a known algorithm called cfrd. And well, they just mention it from yeah. So they just mention it from references. They use this algorithm cfrd, which is used to do the search. So you search on the you search for games that will help you optimize your optimize your policy optimally, which means that your value is being calculated optimally as well. Now, I said that they were networks everywhere. In reality, you can also make the policy a neural network. So if the policy is given a state of the world, produce probabilities over actions, and then sample from those probabilities, you can also make each of the agents' policies a neural network, and again train it using these gradient methods at every iteration. Yeah, so that is what. So this is actually the juice of the paper is in defining this training pattern, because it enables them to first have very few information, expert knowledge about the world, about the game itself, so they don't have to make assumptions on what are good games, for example, because the search algorithm will find good games, and they don't have to go very deep to find good games. So that is actually one of the key factors of this paper, is how they make this search to update their policies and calculate their values. Cool. So the remaining question is, okay, how do you apply a test time? Because of course, when you're training both agents, there are all the proofs there that they will reach Nash equilibrium. But in reality, at test time, you do not know what is the policy of your opponent. And of course, they say that there are unsafe ways to do the search when you do not know the policy of your opponent. Well, of course, they go to show that there are these types of search that don't actually work. But then they come up with the idea of doing a safe search. And this is the part that I find, possibly one of the parts that I find most interesting in the game, is that if you think that the cfrd algorithm, it converges to a Nash equilibrium at every iteration, and then so for that given sub game, you have the optimal policies for both agents. Then you go to the next iteration and you're playing another sub game, and again you find another set of optimal policies, and then you move on and on and on. So at test time, instead of trying to update the policy based on what they see in the world, based on every step, what they do is they randomly sample a policy from all their training data, and they say, okay, assume that both players are playing with these policies, and then they optimize that, and that gives them what is the next best possible action. For the next step of the game, they sample randomly another state of the world, so another public belief state, and they say, okay, now assume that these are the policies that we're playing with. What is my next best action? And they sample from that, and that becomes a safe algorithm, and most of the time it converges to the best possible policy. There are some hyperparameters that you can tune to say, for example, well, do not prefer early iterations because those policies are not as good because they haven't had much time to train, especially if you're using a neural network for the policies. So put more weight on later policies, but at each step you sample from a different policy that you found during training, which is a really interesting approach. And so this is how they set up the training, and because of the fact that you can have like these sub games already sampled in from your training set, and you can find the optimal actions very quickly from those games because you already have most of the things calculated. They actually have an agent that works really quick. In their experiments, the agent took less than 2 seconds to make all the decisions. So on average, it took less than 2 seconds to decide what move to make. So the actions are raise, call, and fold, or there's another game called Liar's Dice, which I'm not entirely sure how it works, but the rules are in the appendix. So it takes less than 2 seconds on average, and maximum 5 seconds. And they pit them against other algorithms, and also pit them against a human expert. And what they see in their results, and is that this REBO, which is how to train the agent, but also how to deploy it at test time, does a lot better than all of the other. So it beats all the other bots, and it also beats the top humans by a large margin. And the other interesting result is this guy here. So what they did is that they said, okay, this is an approximation algorithm. So how good is it at estimating the value? So so they call it exploitability. I had to do a bit of search to see how they call exploitability, but the definition of exploitability of an algorithm is literally the optimal policy. So call it the, oh, sorry. Okay, so the value that you would get from a state following the optimal policy minus the value that you get from the state following the policy that you have currently. Of course, in most cases, we don't know what is the optimal policy, so we can't do this, but there is a way to estimate this. And there's a paper which I don't have at hand, which I'll just post it in the chat. So the paper that I just posted in the chat has this thing called Nash convergence, and that Nash convergence is a good estimate of exploitability. Okay, cool. So
my question,
yeah.
the more comment.
Mm-hmm.
The overall convergence in terms of stealth was actually fairly slow, right? It was always 1 over square root of t, which is like almost like one of the slowest forms of convergence you can have, right?
Yes, that is, yeah, that is the convergence of cfrd, I believe.
And that was the convergence with respect to the value function, like how far off the actual value of the value function you are, or
yeah, I'm trying to find where they define the convergence. But yes, it's slow, but it's still a lot faster than the other algorithms, which is their main selling point.
they probably run it on sufficiently good hardware to make it fast.
Yeah, they actually make a point. They actually make a point that this can be run in very basic hardware. So the inference time, they run it on a single CPU, and actually the hardest part is generating the training data for the value network, because you have to do all this search algorithms for data points to train the value network. That is what takes the longest, and they did use a ton of GPUs for that.
Yeah, but okay. the value networks themselves probably are not particularly complicated machines, right? Because you have only so many input states and output states. It's not like an image recognition network, right? Where you have harder requirements.
Yeah. Yeah. So in the appendix, they put the hyperparameters of the value network, and indeed they're not very deep. It's something like 4,000 units and 6 layers for the value network, which is hyperparameters. Okay. Okay. Yeah. So both the value and policy networks contain 6 hidden layers. Well, I guess with 1,536 units each, right? There's probably a typo.
Yeah. Thanks.
So it's actually not a big network, but yeah, like I said, the what takes the longest is actually to generate the data to train that network. Okay, and cool. Back to the results. They show, so they actually took the time to train a perfect value network, and the perfect value network solves the entire game. So it solves it takes from any state, it takes all the possible actions and calculates all the probabilities until the game is done. So instead of being fixed depth, it goes until the game is over, and it calculates the value of each action. So that is the perfect network, which is cool is good to use if the game is tractable. but if you want the network to work faster, it's not possible to do that. And they compare that to the they compare that the perfect value network computes, so it doesn't use a network, it calculates the value. The full game uses the whole game to calculate to update the value network. And then you have the self-play value network with search, which converges at around here. So this just goes to say that you can actually get good exploitability if you use the search algorithm. If you do not use the search algorithm, you're stuck up here. So the agent doesn't learn anything useful. And yeah, of course, here we have a zoom of the self-play value net, just to show that indeed it does drop. So the exploitability drops almost 1 order of magnitude in the logarithmic scale. So it actually learns something. Cool. So just to conclude, what the paper, so the main contributions of this paper is, first, the framework on how do you convert an imperfect information game into a perfect information game. So this is the change from call it deterministic world states into public belief states, where the players just assume up probabilities of what is the state of the world. And the second big contribution is the way in which they do the search, so they can train their value networks to properly predict what are good and bad outcomes for the game. Cool. So that is this paper. So that is this paper. We don't do much reinforcement learning, but every once in a while, we like to shake things up. Are there any questions? How are the proper probabilities computed for rock, paper, scissors? That is okay. So that refers to the first example. They define what they put at the beginning is it's a toy example. So they say, okay, imagine that you're playing rock, paper, scissors, but actually when a player plays scissors, they get a higher reward than if they play rock or paper. And those probabilities, they are computed manually. So you can manually compute what is the optimal policy for both agents. And it is just to show that even if you can, because you can compute the optimal policy, you can also show that an iterative algorithm will not reach the optimal policy because there's an imperfect information game. I hope that answers your question. Yep. Okay. Cool. So if there are no more questions, thanks everyone for joining us at Paper Club. I'm launching a poll now just to get a bit of a feeling on whether you like reinforcement learning or not. So
thank you very much. That was absolutely great. Really, really nicely presented.
Yeah, I agree.
Thank you. Okay, so just closing remarks. As I said at the beginning, at nPlan, we want this to be a discussion, and we want this to be an open forum for people to talk about papers. So if you have a paper that you would like to talk about, please get in touch with us. All our contact information is in nplan.io. So that's nplan.io. If there's a topic that you would like to discuss or a group of papers that you would like to discuss, send them to us and we will make sure that they are presented. You can ask Dwayne, he has suggested papers. Arvid has presented papers as well, so please do get in touch. And finally, we are presently growing the company. We have open roles in machine learning, in data science, in software engineering. So if you're interested in a career in a rapidly growing startup, please do contact us again in nPlan.io. If you know someone who's interested, please also send them our way. Thanks everyone, and see you next week.
Thank you.
Thank you.